Hello and welcome to Imaging Fast Reactions and Nanoscale Growth. I'm Corey Zarnik, the Imaging Product Manager at Gatan, and we're very pleased today to have Dr. Stach, who's going to discuss the impact of direct electron detectors across the field of materials science. The ability to image reactions in nanoscale volumes directly in the electron microscope at these very high speeds is going to significantly increase our understanding of science, of materials science growth, across a field ranging from catalysis to materials discovery and design. Eric leads the electron microscopy group in the Center for Functional Nanomaterials at Brookhaven National Lab. He received his PhD in materials science and engineering from the University of Virginia in '98 and has held multiple positions as staff scientist, PI for the National Center of Electron Microscopy at Lawrence Berkeley National Lab, and associate and full professor at Purdue, where he retains an adjunct appointment. His research is focused on development and application of electron microscopy techniques to solve a variety of materials problems in nanostructure growth, catalysis, thin film growth, and materials deformation. He's a fellow of the MSA, receiving a number of awards, among them the Eli Burton Award, Purdue's University Faculty Scholar, and Early Career Research Excellence Awards. He's authored over 200 peer-reviewed publications and has given over 150 invited presentations at conferences, universities, and national labs. He also happens to be the co-founder and CTO of Hummingbird Scientific. Tactically today, if we can go to the next slide, Eric.
Certainly. Hopefully.
The format's going to be, you can submit questions through the questions pane. If there are any questions regarding connectivity or the webinar itself, we'll try to address those immediately. And if you have questions for the speaker or myself, we'll collect those and address those at the end of the presentation. So we will be monitoring the presentation for those as we go through. So without any other hesitation, I'd like to introduce Eric, who's going to take us through the rest of the webinar.
Great. Thank you, Corey. So although I've given a number of talks, I guess this is my first webinar, so hopefully it'll go smoothly and I'll do an okay job with it. What I'm going to do here is present more or less the same talk I gave at a AAAS meeting in February, where the goal was to kind of show some examples of how we can use this K2 direct electron detector for imaging nanoscale crystal growth. There's lots of different kind of areas of research that we've been using for this, including liquid cell microscopy, carbon nanotube nucleation and growth. But the one I thought would be most fun to show, because the images are quite pretty and because the science is reasonably well advanced, is my work with Francis Ross and colleagues from the IBM Watson Research Center. So first of all, at the beginning, I want to acknowledge the people kind of working on this with us. Includes Francis, Mark Reuter, and Jerry Tursoff at IBM Watson. Her postdoc, Federico Panchera, and Stefan Hoffman, the sponsor at Cambridge. Dmitry Zaharov runs the instrument here, and then a number of other colleagues, including, importantly, folks from Gatan who helped us develop and work with this camera through the process. So, as I said, I thought of the different types of materials research we've been working on. I thought nanowire growth was a good one to look at, and one of the reasons for this is that they are structures that have a lot of technological interest. People are utilizing these semiconductor structures for a variety of different applications, many of them directly related to energy nanomaterials research. These include electronics and photonics, but also more novel applications in things like thermoelectrics, photovoltaics, and solid-state lighting. What I'll do is show you how we've used electron microscopy kind of over the years, but specifically this camera, to look at different types of processes that occur during the growth of nanowires. Generally, these things are grown by what's called the vapor-liquid-solid mechanism, or sometimes by the vapor-solid-solid mechanism. And what that allows you to do is to use a gold, usually a gold nanoparticle, as a catalyst. I'll show you the kind of processes here in a minute to make these oriented wires. On the bottom right, I have a picture here showing how you can do this with a great deal of control. This is some work from a number of years ago that Francis and I worked on with Cheng-Yen Wen, showing how you can create, one or two atomic layers of germanium embedded in a silicon nanowire through the vapor-solid-solid mechanism. So in this case, we do this in two different ways. At IBM, we use an ultra-high vacuum TEM for this work. What I'll show today is from the environmental TEM here at the Center for Functional Nanomaterials. This is the system we have this camera on at the moment. The idea behind this instrument is it incorporates differential pumping around the objective lens region. This is something that allows us to really go to very high pressures. We can go up to several torr during imaging, and with appropriate heating holders in excess of 1200 degrees C. One of the ways I like to think about this instrument is it's really in some ways the most expensive crystal growth chamber you could possibly come up with. You can actually use this more or less like a standard CVD system. It just happens to be attached to a very nice microscope and a very nice camera. So how does this work? If you take the beautiful kind of covers off and look on the guts inside, you can see that we have, I hope the pointer works, a whole mess of stuff here that allows us to put gases into the microscope. So there's an area here that allows the entry of the gases right around the objective lens region. You can measure the pressures, you can incorporate different types of gases, even measure the reaction streams out here with an RGA. So now I think I might be talking a little quickly, so maybe I'll slow just a little bit. The idea with nanowire nucleation and growth is that basically this vapor liquid solid growth mechanism works as follows. Generally, you'll start off with a small nanoparticle catalyst, here shown kind of in step 1. You can bring the sample to an elevated temperature, and then you introduce a source gas that allows you to provide the growing material to the system. Basically, the source gas is catalytically decomposed by the catalyst and gradually incorporates into the material, eventually liquefying this alloy. And at some point, when you move over into this separate phase region over here, you are supersaturated, which causes the nanowires to both nucleate and grow off the substrate. If your substrate has an appropriate orientation, usually people will use a 1-1-1 orientation. This thing will grow as a nice single crystal, well aligned along the 1-1-1 growth orientation. So a while ago, we had a paper where we were looking at the nucleation process, and as part of this, we made kind of a fun little movie to show this in a little bit more detail. And so here again, you start off with a solid gold catalyst. In this case, we were looking on a silicon nitride substrate, so they did not grow oriented, but rather kind of crawled along the substrate. The idea is the disilane comes in, dissociates, and then begins to gradually incorporate. This liquefies first the outer surface, then eventually the whole material. And as you incorporate more and more silicon into the alloy, it's fully liquefied. And then at some point it actually supersaturates. At a point of supersaturation, you see nucleation and growth. And again, if you do this on an amorphous substrate, the nanowire kind of crawls off and moves off into the side. If instead you do this on an oriented substrate, what you see is these nice nanowires growing in a directed mode. So this is a video taken a number of years ago on the ultra-high vacuum instrument by Sunil Kodambaka, postdoc at the time working with Francis. And again, you see these nice gold droplets. You can imagine the silicon surrounding this, gradually being incorporated into here, and then depositing on the growing nanowire. Okay? So we're interested in lots of different aspects of this growth process, but in particular, because of the images I have, I'll show one sort of small part of this. We've done things like look at step flow at the interface, and this is some work a couple years back where we described how step flow had some control over the compositional incorporation of different materials. We were in particular interested in creating these abrupt heterostructures, the ones where you can incorporate maybe a single layer or two of germanium in a silicon nanowire. And by measuring things like the catalyst, the interfacial step growth rate, you can actually learn quite a bit about this process. So if you look in the upper right, if you have a solid growth, you can have nice slow incorporation of steps, and in liquids it's very fast. And really, with the older cameras, it wasn't fast enough for us to image this. And so this kind of points to the need to go to higher frame rates. This is a general need. This has been something identified in electron microscopy for a while. Another major approach to this is trying to increase the speed of the microscope. There's some very nice work going on in so-called dynamical or ultra-fast electron microscopy. A nice review paper here if you're interested on this, kind of pointing to the need to go to very high time resolutions down into the nanoscale. I like to show this one because it shows lots of different things that are possible down in the nanoscale. But I'd also kind of like to show this because I'm not so sure that it's quite accurate in terms of simply stating that the only thing of interest at the kind of frame rates here are dislocation dynamics. Really, there's a lot more going on. Many thermally and mechanically driven processes in material science, such as crystal growth, sintering, coarsening, and ripening, all the processes associated with dislocation and grain boundary motion and defect interactions are really strongly impacted by the ability to image them at relatively high frame rates down into the milliseconds. So really, as I look at this kind of schemata, I think the thing I've overlaid on top is really the thing that the K2 camera can provide for us. So what is this camera? The idea is that if you have a conventional CCD camera, usually what you do is you have a scintillator that converts the electrons into light, a fiber optic that transfers that down onto your CCD. The problems with this are, well, quite a number. First of all, you can get some scattering in the scintillator. It's a high Z material. You get backscattering from the fiber optic and scattering of light within the optic. There's distortions caused by that, as well as electronic read noise. And so the direct electron idea, it's been around for a while, but there was really a major advance made as part of the DOE's TEAM project. This paper down here is probably the best one to point that out, and it was commercialized by Gatan here. The idea there is that you basically use a camera that allows you to directly convert the electron into a charge. You back thin it. This allows you to have less scattering within the camera itself. And you end up getting quite a number of additional advances. There's limited scattering in the low Z silicon sensor. You remove all the fiber optic problems. You still have read noise, but it's less so. So this has been predominantly used in the area of biological microscopy. Again, this AAAS meeting that was this talk was first presented at, another beautiful talk there from a biological microscopist showing all the ways that it's impacted that field. Really impressive stuff. But what we were interested in doing was trying to push this for high frame rate. You know, if you have an improved detector, right, you can use it to do low dose imaging, or you can increase the dose and use this as a way to do high frame rate imaging. So we worked with Gatan, contracted them out to see how far they can push on this, and they created with this K2 in situ or K2IS camera. The idea here is that you take from the camera the high frame rates, and really you basically incorporate a supercomputer so that you can read them at very fast frame rates. This thing will take pictures at 400 frames per second with 2K by 2K, so really high resolution images. If you want, you can actually run it at 1600 frames a second, where you just stream off the top of the camera and get 512 by 2K. And this is then basically written directly to an array of solid-state drives. We can store up to 4 terabytes in solid-state memory. And we also, importantly, there's a separate loop here that allows you to see some of the images about 8 frames a second, so you can see what's going on. And of course, for real-time microscopy, that's important, because if you just hit go and can't see anything, you may be missing the most important stuff. So this is kind of how this thing works. You can store this into this solid-state drive, again, 4 terabytes worth of data. And then later on, move it to other places. The camera incorporates 3 terabytes of local storage, and I'll show you how we've been doing more than that in the future. I mean, in other ways. So some things to think about. If you have 400 frames a second at 2K by 2K, that's 4 terabytes, and it turns out that we can acquire a total of 15 minutes at 4 terabytes. Right? So that's it's a good amount. We can actually basically use the microscope in the morning, be selective in our data acquisition, and collect 15 minutes of data, and then move it off, say at lunch, a nice long lunch, and then come back and do more work in the afternoon. It takes about an hour and a half to transfer it over to the SAN array. The images that we get are actually raw. There's a kind of a scrambled raw data feed that has to be stitched back into images. At present, with its kind of standard fast desktop, this takes some time, about 40 hours or so. So there's some complications in doing this all. It's still, you know, it's a little bit more complex than just the standard camera usage. All right. There's more than a fast frame rate that's necessary for this. Of course, that's an important part of this, but there's other features that are worth considering and needing to be optimized. You know, I list some of them here. This is kind of a way of looking at the different benefits, right? Not only the high frame rate, but the high DQE. lots of importances in terms of how the detector is built, in terms of fill factor and duty cycle. And I think the bottom one's a noteworthy one. You need to have something that's radiation hard, right? Because you're bringing in high energy electrons into the camera, which can damage the camera. But frankly, we've had this thing now for 18 months or so, something like that, and we're still on the same sensor. So if you anneal it every once in a while, it seems to help recover it, and we've been able to use the same sensor for quite some time. So that's a good thing. Importantly, if when the thing will eventually degrade enough to replace it, and it's not the camera itself, which is the sensor. So some kind of performance metrics forward, we really wanted to have millisecond to maybe even sub-millisecond frame rate. Certainly the best quality. You've got this nice high DQE sensor, right? So you want to be able to count and use every electron. Again, long sensor lifetime so that we don't have to buy a new sensor every 6 months. And importantly, the use of this, creating this high stream of video, and the software was modified to include some rather nice capabilities for doing video stitching and choosing of individual frames, summing of frames if necessary, in order to make videos of high quality. Okay, so here's some images of this. So here's again a gold droplet, in this case at 550 C, rather low pressure of disilane. I'm only going to show this at 40 frames a second. I'll show you at 400 later. It kind of shows that you can collect these things at the 400 frames a second and just choose to display that what you need. But again, with the aberration-corrected images that you obtain, you get very high resolution, high-quality images of this growth process. This will loop back and forth, so you can see things like the individual atomic layers as they are incorporated. You can actually check differences in how the sidewall motion occurs. I'll show you some more details of that in a second. Maybe you can play this one more time. I don't know. When we kind of managed to get this video, I was pretty impressed. It's really hard to believe you can get this level of resolution and stability, as well as detail, out of any microscope, frankly. The high frame rate's helpful too, because if you have some sample drift, you can go through and use cross-correlation to bring that back. In some cases, that's also very helpful. So if we go a little bit further, this is some images taken at this interface with 400 frames per second. And so they're a little bit noisier because you're at a higher level of magnification. Your dose has gone down a little bit, but you still see I think very good quality of the images of the individual atomic layers as they slide on in here and create the new piece of silicon through the growth process. And quick comment here, that's fine. You can take videos, but you can also use these to do lots of analysis. That was an example of the types of things you can get with this. There's more things I think are worth talking about. So our particular system is at this DOE National User Facility, one of the nanoscience research centers sponsored by the Department of Energy. One thing to note is that if this is a capability that you think is of interest to you as you watch, we actually provide this capability notably for free to people who write compelling research proposals motivating it. This puts us in a pretty unique situation, I think. We have lots of different people coming in to gather this data, and then they need to deal with it. And so it's a big data problem that I think is worth talking about a little bit more in detail. One user of ours, John Hart's group from up at MIT, they do nanotube growth, and when they come, it's not uncommon for them to grow something of the order of 10 to 15 nanotube growth runs in a week, generating between 20 and 30 terabytes of data. That's a lot of data, 4.5 million image frames, right? And so one of the questions is just how do you deal with that? In the early stages of this, they just would bring down an 8 to 10 terabyte hard drive, capture some of it, drive it on back up to MIT, download it there, and then send the thing back, and we would move things back and forth. It's a lot of data. And another way of kind of thinking about this data is if you consider the Large Hadron Collider at CERN, it produces 5 gigabytes a second, and that's a major instrument. But the simple, quote-unquote, simple K2 comparison here is that we can generate 4.6 gigabytes a second. So really an impressive amount of data. So if we look at the different transfer times, if you have something like a terabyte of data you need to move back and forth, you can see the ways that it scales with the relative gigabits per second of your data connection. And you know, when you start to get to the 2.5 gigabytes per second, that's not bad, an hour or so for a terabyte. If you need to move this, say, from your computer to a USB drive, say if it's USB 2.0, that same terabyte will take you 13.6 hours to move. There's different types of hard drives, these SATA drives and these RAID drives, and again, you can do different levels of overall storage and transfer with this. Interestingly, we've been doing some things I'll show later about how to transfer directly to different university or national lab campuses, and the best we've done is about an hour per terabyte. Okay, so one of the things that caused us to be interested in going down this pathway was the fact that at the National Laboratory we have lots of interesting resources for big data. Brookhaven is home to the relativistic heavy ion collider, one of the few remaining really high energy physics experiments in America. This thing collides things like 2 gold atoms together and looks at the debris that happens. And as a material scientist, that's about as much as I understand about it. Additionally, though, we do participate in the Large Hadron Collider experiments at CERN. One of the 2 detectors there is the ATLAS detector. It was built here, and actually the data is transferred from CERN to here for storage and analysis. And so if you're at the CFN, you can walk across the street and go to the Rick Atlas computing facility. It's an impressive place, about 2 football fields worth of data storage, and a group of people who are deeply expert in data storage, management, and automated analysis. The unfortunate thing is, as far as analysis goes, they're good at analysis of their own data, and so we've really been relying on them for the data storage and management portion of the activity. Okay? So our data workflow, in the best cases, goes something like this. We have images coming off the K2, the digitizer, stored here at the full 400 frames per second. And then we go through and we use a separate computer to convert those to images, and then we can take these images from the CFM. We put in a 10 gigabyte per second fiber optic from the lab over to Rick Atlas that allows us to move these things over there. They were kind enough to give us half a petabyte of temporary storage. In other words, they gave us some older storage that they couldn't use anymore because it was a little outdated. We actually just upgraded this with another quarter petabyte recently on our own dime. And then we can distribute this through some of the ultra-fast data pipelines if you happen to be at a national lab through DOE ESNet. There's also this thing called Globus Online at Argonne National Laboratory. It's sponsored by NSF, NIH, and other government agencies. And this allows you to both move data to Globus Online and then move it off. We recently did some work with Paul Boyles at Wisconsin and managed to make that work reasonably well. So this is kind of where we are with this, and I think as we move forward, we're likely to do most of our data transfer via the Globus Online. Okay, so next thing we have to worry about is we've got all these images. We have lots of needs to, of course, automate the analysis of this. Those of you all that have done things like particle counting and electron microscopy know that it's not only a pain in the neck, but also can be very, very difficult. You know, in the best cases where you'd have something like a nice heavy gold crystal on an amorphous background, there's relatively robust methods for doing things like particle size analysis or tracking. However, in electron microscopy, the grayscale problems can be subtle and can kind of make this very difficult in some cases. I'm of the opinion that there is an acute need for some form of integrated suite of analysis tools. If you look around, different things have been developed by different folks for their own use, somewhat ad hoc. There's not a lot of uniformity in this. People use MATLAB, sometimes they use Python. There's many other types of processes that are out there. And there's also then associated problems with data formats and analysis codes that work, say, only on MATLAB or other processes that can't be universally applied if you don't have the right software. So this is a recognized problem. It's a problem that impacts many areas of science, including those sorts of imaging and data issues at the synchrotron and neutron facilities. About 2 years ago, there was a workshop run by the DOE to kind of try to link the activities within advanced computing in the DOE and basic energy sciences that kind of identified and recognized these issues. And so what I would say is that our community has identified this and continues to be aware of it, and I think there's real opportunities for many of us to participate and lead activities around the utilization of kind of a uniform set of software methods for this. The nanoscience centers are gathering together here fairly soon to see what we can do. We're also here at Brookhaven standing up a new center for data-driven discovery. We're calling it data sciences for, I forget the full name yet, I'm sorry, I'm blanking. But we're trying to kind of approach this problem in a uniform fashion, not only thinking about electron microscopy data, but also synchrotron data. Some other thoughts on this, maybe getting vaguely controversial. We all know that with the MGI, right, there's a great deal of interest in utilizing big data and understanding how to incorporate big data into accelerating the materials research infrastructure. If you look at the strategic plan for the MGI, right, it incorporates specifically a comment about making digital data accessible, and I think that's a noble goal. Some other thoughts on that. If you look in February of 2013, John Holdren from the White House Office of Science and Technology Policy kind of recommended and more or less demanded that we start to do this, right? So there's an idea of increasing the access of results to federally funded research. And many of you all who are writing your new proposals are seeing an increase in the requirements for your data management and data distribution. So it's, I think, a really interesting opportunity. If we look at some of the data that comes out of these instruments, unique in the world facilities that can produce really high quality data across materials of interest. And so there's some desire from the government to take government-funded research and make it available to, again, maximize the value of taxpayer dollars and also to accelerate materials discovery. That said, this is somewhat of a difficult problem because if you consider the amounts of data, lots of things to worry about. There's lots of things associated with curation of the data, how long to store it, what forms to have metadata in, dealing with things like proprietary formats, all things that are different and complicated to deal with. Additionally, it's expensive, right? So as I say, we just bought 250 terabytes, and it's going to cost me about $60,000 a year to do this. And interestingly, Dmitry Zakharov, whose expertise is in electron microscopy, I'd say he spends about half his time kind of moving data around and transferring it, converting into movies, and helping people through this process. So it's an expensive thing. So I guess my, let's say, somewhat vaguely controversial statements here would be lots of opportunities, but some things to figure out before we really make the impact that's hoped for out of this. So I was planning on speaking for half an hour, and it looks like I hit it. So I think what I showed you was that these cameras allow you to do high spatial and temporal resolution of images that go crystal growth processes that are really astounding. They provide you a massive stream of rich image data, which I think are going to be wonderful for all of material science to have and to analyze. There's some things to be aware of, right? There's some expensive data needs associated with this, including storage and archiving, distribution. And as I say, I think we really need to think about how, as a community, we can advance image analysis and integrated protocols for image analysis and incorporation of metadata and data curating. There's a number of folks with these cameras now, and we've been talking a bit about having a focused interest group at the Microscopy Society of America. So if you find this interesting, perhaps you can join that FIG sometime in the near future. And then one last movie, again showing this at 2.5 milliseconds, just a little gold particle as it comes in and anneals to a larger gold, and you can actually see things like the twins as they anneal out. And this thing kind of subsumes itself into the bulk.